Welcome back to O3 School app. You're welcome back to physics class. Remember, the O3 School app also have its own JAMB app and WAEC app. Please do well to install and also activate the app. All right. In today's physics class, we'll be talking about specific heat capacity. All right. Specific heat capacity. Specific heat capacity. All right. So when we talk about specific heat capacity, it's a very vital topic in science or in engineering. All right. Now, what happens is that when we say specific heat capacity, first, we bring out the word heat. Heat. All right. Now, remember that heat occurs as a result of temperature differences. All right. So we must understand heat and temperature. Temperature. Now, what is heat? We know that heat is the internal energy of a material system. All right. But the average internal energy is temperature. All right. Now, temperature, we all know from our elementary science, is the hotness or coldness of a system or a body. Now, when there is temperature rise, that will give rise to what we call the heat. Now, from Clausius' statement, he told us that heat can only be migrate from a hot body to a cold body. So that means heat is a form of energy. Heat is a form of energy, while temperature is just a property of what? Of matter. It's a property of matter, and it shows the average internal energy of a system. Now, we talk about another thing we need to talk about again is the heat capacity. Before specific, we'll talk about the heat capacity. All right? Now, for heat capacity, is trying to describe the total energy or the energy required to raise the whole mass, the entire mass of a substance by a particular temperature. So the specific heat capacity now is just to raise a unit mass of a substance. All right? What happens is, no matter how we explain, we still have to back it up with what? With formula. So the specific heat capacity is the amount of heat needed to raise a unit mass, a unit, all right, a unit mass of other, I can't say water because we might have other substance like metals, like copper or aluminum, all right? But most students, they said most students go with a unit mass of water. All right. Water is not just a substance. We may have other substance like metallic materials. So we said a unit mass of a what? A substance by 1 degree Celsius. So maybe, for example, let's take water, for instance. Water, for instance, which is the universal solvent. Let's assume we have water molecules in this form. All right. And these water molecules is being heated. Say heat. There's application of heat. All right. Delta H. Now, when there's application of heat, now the mass of this water is 1 kg. But we said a unit mass. So if it's 1 kg. Now let's assume before, if we increase the temperature, but initially, let's say it's at 28 degrees Celsius. All right. Now, specific heat capacity is telling us that the total amount of energy needed or the energy required to raise a unit mass of this substance from 28 degrees Celsius to 29 degrees Celsius. All right. So that means there's an increment of what? 1 degree what? Celsius. So that means, let's have, I have these water molecules in another stage. All right. Now, application of what? Of heat. Now, when we apply 1 degree Celsius, this value from 28 degrees Celsius increase to 29 degrees Celsius. So there's a unit rise. All right. I mean, there's an increment of what? Temperature by 1 degree what? Celsius. So we are being specific. Now, when you talk about heat capacity, we talk about the entire what? The entire mass. The entire mass of that substance. All right. But for specific, a unit mass is peak from that entire mass. All right. So specific heat capacity, all right, is the energy needed, or is the amount of heat needed to raise 1 unit mass of a substance by 1 degree what? Celsius. Or either 1 degree Celsius or by 1 Kelvin. All right. So let's see. We can say that for heat capacity, H is heat capacity. All right. And C is specific heat capacity. All right. Now, we know that the quantity of heat, Q is quantity of heat. Quantity of heat. Now, if the quantity of heat is directly proportional to the mass, the quantity of heat is directly proportional to the mass and also directly proportional to the what? Change in what? Change in temperature. All right? So that means that, for example, if we need to raise the temperature of water in a drum, all right, that means that we need higher quantity of what? Higher quantity of heat. And one thing about water is that for you to raise the temperature of water by 1 degree Celsius, we need about 4,200 joules of energy. All right? So that means water have very high specific heat capacity compared to other metals. That is why for water to boil, it takes time because the water has to absorb heat up to 4,200 joules per degree rise in what? In temperature. Unlike other metals, if we apply heat on a particular metals, the metal, they absorb heat immediately because metals, they have free electrons. All right? We're made to understand from the band theory that the energy gap between the valency band and the conduction band of metals, they are very close. So the electrons in metals, they are free to move apart. Now, the quantity of heat is directly proportional to the mass and change in temperature. All right? So Q is equals to Cm delta theta. Where this C is the specific heat capacity. All right? So specific capacity is quantity of energy or heat needed to heat that particular material over the mass, then change in what? Change in temperature. So that means that the specific heat capacity is independent of the mass, while the heat capacity depends on the mass. So specific capacity is quantity of heat over the mass of substance, then change in temperature. We know that change in temperature is θ2 minus θ1. All right? Initial temperature and final temperature. From the previous example I did on the board, we have 27 degrees. All right? The water was initially at 27 degrees. There was an increase in temperature for 1 degree Celsius. It moves the water from 28 to 29. So definitely, we can say 29 minus 28. That will give us 1 degree what? Celsius. That's the increment in what? In temperature. All right. So as I've earlier said, H is heat capacity, and that heat capacity is the amount of heat needed to raise the entire mass of that substance by 1 Kelvin, either by 1 Kelvin or by 1 degree Celsius. Then C is the specific heat capacity. Mind you, materials have their specific heat capacity. All right, let's see some material have their what? Specific heat capacity. For water, we know that water is 4,200 joules. Okay. Now, we know that C is Q over M, C change in theta. Sorry, M change in theta. All right. So that means C equals to Q over M change in theta. Now, the quantity of heat is measured in joules. So joules, mass is measured in kilogram. All right. Temperature is measured in Kelvin. So specific capacity is joules, kilogram inverse, Kelvin inverse. Kilogram inverse, Kelvin inverse. That's the unit. So we can say that C equals to joules per kg, right? Joules per kg, K. All right? So Q is what? M change in theta. So we can say joule per kg, K. All right? So that is the unit of specific heat capacity. Now, which other thing again? We have, all right, we have substance like aluminum, copper, water, gold, iron, ethanol, hydrogen. So aluminum is 900, copper is about 387, water is 4,200, which is popular, gold is 129, iron is 452, ethanol is 2410, and hydrogen is 1415. So hydrogen is about 14,105 joules per kg degree Celsius. Now, why do I highlight all these substances out? For example, if we intend to boil water, all right? If we intend to boil water, and we intend to place aluminum or copper inside a burning fire, what happens is that the aluminum particles or material, the electrons in them, they are free. All right. So what happens is that the aluminum will heat up, we absorb heat immediately. A material that absorbs heat immediately is as a result of the fact that they have very little or very small specific heat capacity. The specific heat capacity of rubber is so small that rubber gets easily absorbed by heat easily. All right. Now for water, water for 1 degree Celsius, it will take about 4,200 joules. That is why while boiling water, it takes some time before the water heats up. What happens is that for every degree rise in temperature, about 4,200 joules is needed. All right. Now for iron is about 452. That means it has a very low specific heat capacity compared to water. So iron will heat up very easily. So most questions will be asked from your JAMB and WAEC. All right. So what you do is that you have to know the decrement in the value of specific capacity will tell you if that material will absorb heat immediately or not. All right. So if the material has a very high specific capacity, it will take time for the material to absorb heat. All right. So there is one popular experiment whereby we have balloon filled with air and balloon also filled with water. All right. What happened is that the one filled with air, remember the balloon is made up of rubber and is filled with air. What happened? It blasts or it bursts very fast. The reason, because when something of this nature, let's assume this is balloon for instance, then we apply heat, delta H. When you see delta H, that is heat content. So when we apply heat, here there is water content, H2O. Here you have maybe just air. All right. Now what happened is that rubber has a very low specific heat capacity. It will absorb heat immediately, and that's why it explodes. But considering water inside the balloon, the water has very high specific capacity. All right. So what happened? The water will try to retain heat for a very short period of time. All right. Because for 1 degree Celsius, there is need for 4,200 joules of energy. So what happened is that the one with air will explode or blast easily when heated up compared to the one that has water. Okay, so let's check that of hydrogen. Hydrogen is about 14,150. Yes, hydrogen has a very large what specific capacity, and that is why water also contains oxygen and hydrogen. Another reason why this balloon with water will not explode easily is because it's water, and water is also made up of hydrogen and oxygen. Now, what happens? The hydrogen content in water is also much. Imagine hydrogen is about 14,150. All right? So, water contains hydrogen bonding. The intermolecular forces that makes up water, right? With hydrogen content, they have high intermolecular forces. And that's the same reason why this will not explode easily. Okay. Now, remember that the specific heat capacity, it calculates the amount of energy stored in a system, in a body, all right? Or the energy released from a system as temperature changes, all right? As temperature changes. For 1 degree, for a unit mass of substance, for 1 degree Celsius or 1 degree Kelvin. So the amount of heat needed to raise, all right, to raise a unit mass of what? Or substance. That is the specific heat capacity. Okay, let's move ahead. Now, remember that Q is the quantity of heat. All right? Q is the quantity of heat. Most questions that will be asked is to find the quantity of what? Of heat. All right? As I've earlier said, substance and their specific capacity, iron is about 450, copper is about 385. So water has a very high specific heat capacity, which is why it slows up while heating. All right? When you heat water, it slows up. And that is why most times, if you even check for the coolant system of a vehicle, of a car rather, what do you need? There is need for water. All right? The reason is that water cool up slowly. That is why water is used as what? As a coolant in most vehicles. All right? That's another reason. The reason is that it will take time for water to heat up when used as a coolant in any motor, in any vehicle. All right? The reason is that water has a very high specific heat capacity. Now we have methods, we have ways of determining specific capacity. All right, we have the continuous flow. We have the electrical method. We have the calorimeter method. All right. This calorimeter method is just telling us that it's just a principle. What's that principle? It's telling us that in an insulated system, when we mean insulated system, that means that system, a little amount of air in that system does not have any space to escape to the surrounding. All right, that's an insulated system. So what calorimeter method told us is that in an insulated system, the heat loss is equals to what? Is equals to heat gain. All right, heat loss is equals to what? Heat gain. Then we also have the electrical method. Electrical method means you are supplying electricity to that system. So the electrical method is used to determine the specific heat capacity. Remember that we can get heat energy, or electrical energy can be in form of heat. All right? Electrical energy can be in form of heat, power times what? Times time. One effect of electric current is heating effect. Your electric cookers, your iron, your television, as you use them, all right, for maybe for 1 to 2 hours, based on service utility, what happens is that they generate heat. So electrical energy can be in form of what? In form of heat. And that is power times what? Times time. Now remember that power is current times voltage. Power is current times voltage. Remember we have mechanical power and electrical power. All right? When you see current times voltage, that is electrical power. So what happens is that electrical energy now becomes what? P, T. And PT becomes what? IVT. All right? So for example, the electrical method is mostly used to check or to determine the specific heat capacity of solid like metals, aluminium, coppers, zinc. All right? That is what the electrical method is what is used for. Now, when you talk about the continuous flow is to check fluid in a narrow pipe. All right? Is to check heat flow in a what? In a narrow pipe. So that means that if the quantity of heat is equals to MC change in theta, now heat in form of electrical energy will become, that means Q now becomes IVT. Now, so we have IVT. That implies that IVT is equals to what? MC change in what? MC change in theta. Now, most of the questions that will be asked in your JAMB is relating to this electrical method, all right? Whereby all other parameters will be given to you, and maybe you'll be looking for the time taking, all right, for that quantity of energy to be passed through a particular setup, maybe a bomb calorimeter. The bomb calorimeter is mostly used in in a chemistry lab, for example, to determine the fuel combustion, all right, the heat content needed to burn a particular material, all right? So IVT equals to MC change in theta. So as I've earlier said, the calorimeter method is called the mixture method. And that mixture method is trying to tell, is a principle based on that the heat gain is equals to what? Heat loss. And that's in a system, and that system must be what? Insulated. Insulated in the sense that there is no there's no heat loss to the surrounding, or there's no heat absorbed by the system. All right? Okay, so we can also have some formula relationship in this form. In this form, we know that C becomes IVT over what? Over M delta theta. Where delta theta is T2 minus what? Minus T1. All right? So this is specific capacity is equals to energy supplied over the mass times change in what? Times change in temperature. Now, there are some things we need to note again. All right? It is a substance with high specific heat capacity, this C. Substance with high specific heat capacity, they heat up slowly, as I've earlier said before. Substance that have a very high specific heat capacity, they heat up slowly. That is why water is used as a coolant in most vehicles. Now, substance with low specific heat capacity, they heat up very fast. All right, they heat up quickly. A good example is metal. If you place metal on fire, it heats up very fast, because they have very small specific heat capacity. All right, so let's see a problem. To have a problem, he said, how much heat is needed to raise the temperature of 2 kg of water, H2O, of water, from 20 degrees Celsius to 30 degrees Celsius. How much heat? All right? So we need the quantity of heat. That means Q is MC change in what? Theta. Q is MC change in theta. So the quantity of heat, we have the mass. We have 2 mass, so 2. Now the specific heat capacity of water, once you see water, is 4,200. All right? Now there's a change in temperature, theta 2 minus what? Minus theta 1. So Q becomes 2 times 4200, 30 minus 20. So Q becomes, we have 0048, all right, times 10. So that becomes 84000. So we can move 1, 2, 3, 4. So that's the quantity of heat is about 8.4 times 10 raised to the power 4 joules. All right, 8.4 times 10 raised to the power 4 what? Joules. That is the quantity of heat that is needed. So, as I've earlier said, in the electrical method, all right, in the electrical method is commonly used in most of the chemistry or physics lab to determine the specific capacity of metals like aluminum or copper using electrical energy. All right, so let's see the electrical method. The electrical method, all right, to determine the specific heat capacity, of solid, all right, like metals, such as what? Aluminum, iron, or maybe even zinc. Aluminum, iron, or what? Or zinc. All right? The principle is that the energy supplied is equals to heat energy required, or heat energy gained, all right, by the metal. Now, what happens is that we know that for metals, when metals are heated, either by electrical methods, all right, either by electrical method or by the calorimeter method. Calorimeter method is just based on maybe a hot body and a cold body, all right? Now, based on the electrical method, energy supplied is equals to heat energy gained by the metals. Now, we're made to understand that when heat is applied to a metal, what happens? The metal expands. And before expansions, what happens is that the molecules of that metals, they vibrate. And when they vibrate, electrons, they migrate from one point to what? Another. the electrons, they agitate, migrate, all right? Now, the energy supplied is equals to heat energy gain by the metals. And we know that electrical energy E is power times time, all right? If energy is power times time, that implies that the heat energy gained by metal is Q. And we know that Q is MC change in theta, all right? So that means that PT is MC change in theta. Now, sometimes you'll be asked to calculate the power, all right? You have to calculate the power supplied to the system. So that means power is now MC change in theta over time, all right? Power now is MC change in theta over time. Now, sometimes you may be asked to find current. If you're asked to find current, that implies that power is IV, all right? Power is IV. So IV is equals to MC change in theta over time, all right? So we can divide both sides by V. So current is MC change in theta over VT. So this is so this is the current supplied to that system. So the principle is just based on the fact that the energy supplied is equals to the heat energy gain if we are using the electrical method. If we are using the electrical method. So to determine the specific heat capacity of solid, you use the electrical method. All right? Okay. That is that on the electrical method. Then we also have the calorimetry method. All right. Now, in this method, the principle is based on what? Heat gain is equals to the heat lost. All right. For example, I have a cold water poured inside a hot water. Those are two mixtures. All right. Now, if I have a hot water poured to a cold water and the system becomes sealed, become insulated, covered, whereby there is no form of air that is escaping, all right, or there's no form of heat that is escaping from that system, we're made to understand that the heat gain is equals to heat loss. Heat gain is equals to heat loss. So that means, let's assume we have a hot solid rather, and a cold water. We have a hot solid. Let's say this solid is copper. All right? Let's say it's copper ions or copper. Then we have a cold water, which is H2O. All right? Now, what happened is that the calorimeter method is used, whereby we know that becomes MC into TS minus TF. That means, what is this? Remember that the quantity of heat is MC change in theta. So M, mass of solid, specific capacity of solid, all right? Temperature of solid and final temperature. Then equals to the mass of water, specific capacity of water, final temperature minus temperature of what? Of water. Mass of water, specific capacity of water, mass of solid. So what we are saying is that the heat gain by this hot solid is equals to the heat gain by the water. That is what the principle is telling us. All right. So MS is mass of solid. All right. CS is specific heat capacity of solid. All right. Then TF is the final temperature. Final temperature when both hotness and coldness, they now mix together. They are now in thermal equilibrium. So when they are now in thermal equilibrium, we now have a final what? Temperature. All right? Then we have TS. TS is the temperature of solid. TS is the temperature of what? Of solid. Then we have TW. TW is the temperature of what? Of water. Temperature of water. All right? Then CW is the specific heat capacity of water. So that is what the principle is telling us. So specific heat capacity is not measured directly by a single meter. We don't have a single instrument. It's either you use the calorimeter method, that's the mixture of mixture, right? The mixture of two substances in different temperature stage, a hot solid and a cold water. Or you use the electrical method. All right? So there's no specific instrument used to determine specific heat what capacity. Rather, they are based on the experimental observations, either by calorimeter method, the continuous flow method, or the electrical method. Okay. Now, one thing we need to know again is that we need to really understand the difference between heat capacity and specific heat capacity. All right? We really need to understand is that this is H and this is C. All right? This H is heat capacity. And C is specific heat capacity. All right? For this one is to raise the temperature of the whole body. The whole body. All right? Why this one is to raise the temperature of a unit mass. A unit mass. What is that unit mass? All right? The unit mass is 1 kg. Now, we are raising a whole temperature of the entire substance by 1 degree Celsius. Why this one? Just a unit mass of that body by what? By 1 degree Celsius. So that means that the heat capacity depends on mass. So heat capacity depends on mass. All right? Heat capacity depends on mass. What does that mean? More mass, it means that if we have more mass, if we have more mass, that means that body has more particles. All right? More particles. More mass means more particles. Now, as big that body is, if we need to raise the temperature of that body, that means we need more heat. We need what? We need more heat. A drum filled with water, we need to raise the temperature of that drum. All right? It will require what? More heat. Why more heat? Is because the body has more mass. And a body that has more mass, that body has more particles. You must put that into what? Consideration. So that means the heat capacity depends on the mass of that body. It depends on the mass of that substance. All right? Why specific? For specific heat is independent on mass. Is independent on mass. Specific capacity is independent on mass. All right? Because the reason is that the specific capacity is independent of mass. It's just a property. All right? It does not relate to the magnitude. It does not tell us about the magnitude of the material. All right? It's just telling about the property of the material, not the magnitude of the material, not the size of the material. Specific. All right? The specific is not telling us about the size of the material, Rather, it's telling us about the property of the material. All right. So if the quantity of heat look at it now, the quantity of heat is directly proportional to the mass. So that means more mass, more heat. More heat, more mass, because it is directly proportional. All right. So that means that more heat needed to raise temperature. If we have more mass, that means we need more heat to raise the what? To raise the temperature. All right. Okay. So let's see some problems. Let's see some problems. We have one. Okay. Now we have a question. It said, let's see. The question says, suppose voltage is 12 volts and current is 2 amp and time is 30 seconds and mass is 0.5 kg and change in temperature is 20 degrees Celsius. So we have to find C. All right? We have to find C. What is C? C is the specific heat capacity, the amount of heat needed to raise the unit mass of what? Of a substance. All right? Of a substance. It could be water, it could be metal, by 1 degree what? By 1 degree Celsius. Now, the question involves voltage and current and time. What comes to our mind? That is the electrical method of determining the specific heat capacity of a substance. All right? So what happens? We know that power times time is MC change in theta. All right? Power is current times voltage. Power is current times voltage. So that means IVT, all right? It means that IVT is equals to MC change in what? Change in theta. IVT is MC change in theta. So what does that imply? We have current, we have voltage, we have time. So we need C. So C becomes IVT. C is already here. So M change in what? Change in theta. So the specific capacity, current is 2, the voltage is 12, times the time. Time is 30, all right? The mass is 0.5. Change in temperature is what? Is 20. So 0 can cancel 0, 2 can cancel 2. So what do we have? We have 12 times 3 over 0.5. All right? So automatically we can have 12 times 3 over 5 times 10. If we do that, 5 here 1, 5 here will give us 2. So that's 12 times 6. So I think that should give us 72. What do we have here? Okay. So that's about 72. So we have 72 joules per kg K. So this is the specific heat what? Capacity. This is the specific heat capacity that is demanded. All right? So remember that on the calorimeter method, that the heat loss is equals to heat gain. When two bodies at different temperatures are mixed, maybe we have hot body and cold body, in an insulated system, the heat lost by the hot body, all right, because the heat will be transferred from the hot body to the cold body, as stated from thermodynamics law, which we call the Clausius statement. We have the Planck statement, we have the Clausius statement. So the heat lost by the hot body equals the heat gained by the cold body. That is on the calorimeter method. All right, so let's see question from our app. Questions from the JAMB app. So let's see from the JAMB app. Okay. All right. 2012. JAMB 2012. Question 22. It says calculate the temperature change when 500 joules of heat is supplied to 100 grams of water. All right? So that means the specific heat capacity, all right, is C, is 4,200, all right, joules kg, K inverse, all right. Then the quantity of heat, we are told that is 500 joules, all right. Then we have to find change in temperature, is unknown. Then the mass is 100 grams. That's 100 over 1,000. 0 will go, 0 will go. So we have 0.1 kilogram. All right? So you do this first. The mass is in gram. You convert to kilogram, because if you check the unit of the specific capacity, it's coming with kilogram. So the unit has to be uniform. So kilogram. So what's the next? The quantity of heat is MC change in theta. All right? So change in theta, because the question says calculate the temperature change. Now the temperature change becomes the quantity of heat over the mass times the specific heat capacity. So what's the quantity of heat? We have 500. What's the mass? 0.1 times 4,200. So 2 of these 0 will go. So we have 5 over 0.1 times 42. So let's see. Okay. Automatically, if you move here, cancel this 0. So that's about 4.2. All right. So change in temperature is 5 over 4.2 degree Celsius. So 5 divided by 4.2. So that's about 1.2. So change in temperature is 1.2 degree Celsius. The change in temperature is 1.2 degrees Celsius. So let's see. Option A, we have 12.1. B, we have 2.1. C, we have 1.2. So the correct answer is what? 1.2. Okay. So the correct answer is 1.2 degrees Celsius. All right, we have another question. This is on 2017. JAMB 2017, question 21. Question 21 says, which of the following units is the SI unit of heat capacity? Heat capacity. All right, heat capacity is what? There's no mass. So it's C change in what? C change in what? Change in theta. So the correct answer there is just C. All right? We have a C. The heat capacity of a substance is the amount of heat required to change its temperature by 1 degree and has a unit of energy per degree. All right? Energy per what? Energy per degree. So the correct answer there is C, and it's J K what? K inverse. All right? JK what? K inverse. So the correct answer there is C. The specific heat capacity, if it's specific, it would have been Q equals to MC changing in theta. All right? But they're asking for what? For H. All right? H. For H is equals to what? Quantity of over what? Over change in what? Change in temperature. So that is joules, Kelvin what? Kelvin inverse. So the correct answer there is C. Okay, let's see again. We have 2022. Question 23. It said, what is the quantity of heat? What is the quantity of heat required to raise the temperature of an object of 600 grams by 4 degrees Celsius? If the specific capacity is this, what is the quantity of heat? All right? So we know that quantity of heat is MC change in what? Theta. So quantity of heat, what's the mass? The mass is 600 grams, so you divide by 1,000. All right? The specific capacity is 650 times, it said, if there's a temperature rise of 4, so 4, all right? So 0, we cancel 0, 0 cancel 0, 0 cancel 0. So Q becomes 6 times 65 times 4, all right? So that was what you have. So that's about 1260. So 1260 joules. You have 1260 joules. Let's see. 6 times 65 times 4. So, you have 1560. So you have 1560 joules. So that is the quantity of heat. All right? So let's move ahead. Okay. This one says, a block of aluminum is heated. Calculate the heat capacity. That's 2015. Question 14. A block of aluminum is heated electrically. Is heated electrically by 25 watts. So power is 25 watts. Now, if the temperature rises, there's a change in temperature of 10 degrees Celsius in 5 minutes. In 5 minutes. So that's the time. Time in 5 minutes. Calculate the heat capacity of the aluminum. All right? So heat energy is equals to heat capacity times temperature difference. All right? Heat energy is equals to heat capacity times. So that means, remember that heat capacity is equals to heat energy over change in what? Temperature. All right? So the question says, calculate the heat capacity. So what is the heat energy? Now, if you check, let's say heat capacity is X, all right? So X, the heat energy. Now, the heat energy is coming as a result of supply of electrical energy, all right? So that's power times time over change in what? Temperature. From electrical method, all right? When there is heat loss as a result of electrical energy, because you are supplying electrical energy, definitely there will be heat loss. Now, there will be heat gain by the metal, because the electrical method is mostly used to determine the specific heat capacity of solid, aluminum, iron, any form of metals. So what is the power? The power is 25. What is the time? The time is 5 minutes. So because the time is 5 minutes, we have to convert it to seconds. You multiply by 60. All right? So 5 times what? Times 60. Now the change in temperature was given to be what? 10. So we have here 10. 0 cancel 0. All right? So we have 25 times 5 times this. We have, all right? So let's see. What are the given options? Okay. So that's about 750. All right? That's about 750. That's the heat capacity. And it's Joule. Joule's what? Kelvin inverse. Joule's Kelvin inverse. So that is on JAMB 2015, question 14. Okay. Sorry. I think this one is 2008. 2008, question 22. 2008, question 22. Okay, we have another question. I think this is on 2016. We have a question from 2016. JAMB 2016, question 43. It said a block of aluminium is heated electrically. A block of aluminium, all right? The specific heat capacity of metals like aluminium can only be obtained by electrical method. But when it involves mixtures, use the calorimeter method. All right, so it's heated. It's heated, so power supplied to the system is 30 watts. Now it's heated. Now if the temperature rise, I think it's similar to the one we did before, 2016, 43. There's a change in temperature of 10 degrees Celsius. All right, time is also in 5 minutes. 5 minutes. Find the heat capacity, all right? So heat capacity is equals to energy supplied over change in what? Temperature. Now, what is this energy supply? It's power times time now. So power times time over change in temperature. So let's say here is X again. So S, what is the power? 30 times 5 times 60. Because 5 minutes to seconds, you multiply by what? To seconds, you multiply by 60. All right? We are converting minute to seconds, you multiply by 60. Temperature rise is 10. So 0, we cancel 0. So S becomes 30 times 5 times 6. S becomes 30 times 30. S becomes the 900 joules per Kelvin. All right? Joules per Kelvin. So the correct answer there is C. We have another one from 1997. JAMB 1997, question 17. It said, equal mass of copper and rubber are raised to the same temperature. After some time, the copper was observed to be at a lower temperature because A, the specific heat capacity of copper is lower than that of rubber. B, copper expands more than rubber. C, the specific heat capacity of rubber is lower than that of copper. D, rubber expands more than copper. All right? So the correct answer there is A. The specific heat capacity of a substance is the amount of heat needed to raise the temperature by 1 degree Kelvin. All right? So if equal masses of copper and rubber are raised to the same temperature, the copper will cool down faster than the rubber. All right. Now, if the specific capacity of copper is lower than that of rubber, this is because a substance with lower specific capacity requires less heat to increase it. We have said it before. So, and therefore also heat loss fasters. Materials that have less specific capacity, they lose their heat more faster. So the correct option is that the specific heat capacity of copper is lower than that of what? Rubber. The specific capacity of copper is lower than that of rubber. The reason is that the rubber, the electrons in rubber, right, they are bounded to each other. But that of copper, the electrons are not bounded to each other. They move freely. And that is why those metals, they lose their electrons very fast. Okay. All right. So that will be all for this video. See you in subsequent class. All right.